So good morning everyone. So welcome to week 12, the extra live interaction session for the course Fabrication Techniques for MEMS-based sensors from the clinical perspective. So I'm the course TA, Rayan Jisma. This is about me. So in this week, what we will do is we'll just have a quick recap of the content that is covered during the entire duration of the course. Some of the topics that we will go through are particle contamination, cleaning methods, photolithography, etching and deposition techniques. So first is various contaminants. So we know that there are different clean room standards. So the clean room standard will tell us how much uh, how much number of particles are present. So clean room is generally a controlled environment where we have a fixed number of particles having particular dimensions. So the number of particles are reduced by having specialized equipment like HEPA filters and so on. So here we have adopted various methods to maintain the clean room in a uh, clean room as a controlled environment. However, there may be various contaminants that may be present. So some of them are one is ionic material. So this can be ions such as sodium or potassium, or molecular compounds, or it can be elemental particles or airborne dust. So depending on what kind of contamination we are having, the performance of the device will get affected. So that is why it is very important that the device has to be fabricated in strictly clean conditions. And also for that, what we will do is when we start with the fabrication process, we will start with cleaning of the sample. So first is let us look at particle contamination. So if there is any particle contamination, what will happen is there will be any defects in the pattern that is generated that you have made on your sample. There can be other effects such as breakdown of the film and so on. If there is, in order to remove the various contaminants that is present on the sample, we have various cleaning methods. So one of the cleaning method that we have is piranha cleaning. So piranha cleaning, it is based on the name of a fish. So that it which will attack in herds and it is quite ferocious. So this cleaning will remove all the organic residues, and we generally use H2SO4 and H2O2 in the ratio of 3:1 to 6:1. So here, larger the concentration of H2O2, more vigorous the solution is. So 3:1 will be a highly vigorous solution when compared to 6:1. Then this solution is a exothermic process. So again, when you mix these two chemicals, there will be a lot of heat generated, and the solution will become hot. So as time goes, the reactivity of the solution will start to decrease. So what happens is, when the two components are mixed, nascent oxygen will be released. This will oxidize the organic molecules. So wafer can be dipped in this solution. Since nascent oxygen is released, there will be some thin layer of native oxide that is formed on the surface of the wafer. So what we generally do is, after we do piranha cleaning, we'll go for a HF dip in order to remove the SiO2 layer. One important thing is that SiO2, silicon dioxide, is hydrophilic. Means it is moisture loving. whereas silicon is hydrophobic. It hates moisture. So, after the dilute HF dip, we can know whether if we are having a silicon sample, we can know whether it is cleaned by checking whether the wafer is hydrophobic or hydrophilic. So, if it is hydrophobic, means the oxide is completely removed in the HF dip. If it is still hydrophilic, that means some amount of oxide is still present. Is this clear? Now, let us move on to another type of cleaning called RCA1 and RCA2 cleaning. So, here we have two types of cleaning. RCA1 is generally used to remove organic contamination. RCA2 is used to remove inorganic contamination. So, what happens is, like in RCA1, we use ammonium hydroxide with H2O2 and water. So this solution will be heated and the wafer will be dipped for some time. If there is any metal that is present in the sample or any organic material that is present in the sample will get removed. Then like in RCA2, like once the wafer is cleaned using RCA1 cleaning, we will then go for RCA2 cleaning, where we use hydrochloric acid with H2O2 and water. Here, the metal ions will get converted into hydroxides or chlorides. So this is then again removed from the uh, removed from the sample. So the wafer then becomes clean. So if you want to know whether the wafer is clean or not, then like I told before, if it is a silicon wafer, one of the primary indicator is that there will not be any water that is sticking to the surface. This is because silicon is hydrophobic, so it does not attract any water particles. And the ratio that we use for cleaning will depend on the like how much severity of the cleaning is used. So this is generally the first cleaning process, that is. So next, another topic that we saw in class was oxidation. So oxidation, like there are two types of oxidation. One is dry oxidation or wet oxidation. So in dry oxidation process, we will just oxidize the sample by passing it through O2. In wet oxidation, we'll use water in order to oxidize the silicon wafer. So what in both both will happen at high temperature around 800 degree to 1000 degree. Oxidation process to happen, the temperature has to be really high. Okay. In the dry oxidation process, silicon will get combined with oxygen to form SiO2. In the wet oxidation process, SiO2 is formed as well as hydrogen gas is also formed at high temperature. So, whether it is dry oxidation or wet oxidation, what happens is the silicon dioxide will um, it will grow on the surface of silicon, and like what happens is like there is something called as the pilling bedworth ratio. as the volume of silicon, the molar mass of silicon dioxide is larger compared to that of silicon. What happens is the silicon dioxide that grows will occupy more volume compared to the silicon substrate. Like so, some when the oxidation is starting, we'll have a silicon wafer like this. As silicon dioxide grows, like it will start to react with silicon on the surface. So what will happen is oxygen has to diffuse through the interface and reach with the silicon, and it will react with silicon to form SiO2. Then if we are having a thin layer of SiO2 on a sample, what happens is the oxygen will have to diffuse through the SiO2, reach the silicon and react with the silicon. So the film starts to grow inwards. Silicon, as time goes, the SiO2 film starts to grow inwards. So what happens is it will consume some amount of silicon layer, and how much it consumes is it will consume at least 0.44, that is 44% of silicon. So this value is calculated based on the Pilling Bedworth ratio, and it will consume for 44% of thickness of silicon. However, like it will grow additionally 56% above the silicon layer. Okay. So, like once we have a wafer, we also saw how to do oxidation. Next, we will look at photoresist. So this, like photolithography in general. We want to pattern wafer in order to make different patterns on it. In order to pattern wafer, we use either a mask or an intermediate layer on which patterns can be transferred. So this is an intermediate layer which is photosensitive. Here you can see this is how a photoresist will look like. So this photoresist is composed of various components such as polymer, solvent, sensitizers, additives. So polymer is like the main component. Like we have seen one method where we have grown oxide on the silicon surface. If you want to pattern, make any patterns on your substrate, then we need to have some kind of intermediate layer, which can be used to transfer patterns. So this intermediate layer is a photoresist. It is photosensitive, and this is how it will look. And it consists of different components. So like the various components that are present in the photoresist are polymer. So this will change in structure. Then we have a solvent. So in order to make the photoresist have some like consistency, we are having solvent. We also have sensitizer, so which like undergoes some kind of chemical reaction when we are exposing it to a particular wavelength. So the photoresist is generally very sensitive to exposure to UV wavelength, and there are different lines of exposure is used. One is 365 nanometer is one of the commonly used wavelength in order to expose photoresist. So what happens is when we are exposing the photoresist to UV light, the sensitizer will have, like these sensitizers are also called as photoactive compounds. So like they will undergo some change in their chemical structure. Because of that, what will happen is their ability to get dissolved in a developer will change. Okay, so there will be certain additives as well. And there are different types of photoresist. both positive and negative photoresist. So in positive resist, the exposed region will get dissolved. In negative photoresist, the exposed region does not dissolve, remains. So remaining region will get dissolved. So what happens is in negative photoresist, the exposed region will undergo some process called as cross-linking. As a result, it will not get dissolved in the developer. However, the remaining regions will get, which are not exposed, will get dissolved in a developer. So if you look at the general photolithography steps, first is we have to prepare the surface of the wafer. So what we'll do is we'll do cleaning. Generally, this is solvent cleaning. So we'll use acetone, IPA, and DI water. Then we'll dry the water surface. Like it is important to have a dry and clean surface. Otherwise, there will be issues in the photoresist adhesion. Then we'll apply a thin layer of photoresist to the wafer. This is done using spin coating process. Before exposure, we want to like reduce the amount of solvent that is present in the photoresist. So for that, what we will do is we will try to partially evaporate the photoresist solvent. This is done for lesser amount of time. In the next step, we will align a mask to the wafer and we will expose the wafer to UV light. So, like I told before, positive resist will get dissolved in the after like positive. If it is a positive resist and if it is exposed, then in the developer it will get dissolved. Whereas negative photoresist will get polymerizes. Then in the development, we will try to remove the unpolymerized photoresist. So in the development process, we will have some regions where there is photoresist present. So here photoresist is present, but there will be some regions where we can directly see the wafer surface. Then if we want to go for metal deposition, we will just directly go for metal deposition. So this metal or generally a metal deposition. Then if you want to go for etching, then we will go for hard baking. Okay. In the case, if you want to do metal deposition and lift off, then there is no need to do hard baking because in metal deposition and lift off, what we generally do is we'll deposit metal everywhere and then we will try to dissolve this in the solvent. So what happens is wherever photoresist is present, it will get dissolved in solvent. So in those places, the metal will get lifted off. So in the end, if you are going for metal deposition, what you will be left is with a wafer, and you will have metal in some region. So in those regions where there is no photoresist present, you will have some metal. Whereas in the regions where photoresist is present, your metal will get lifted off. So this is what happens in metal deposition. If you are going for etching, what will happen is you have to make your photoresist very hard. So you will do hard bake where you keep the sample on a hot plate and heat it for a specific amount of time. So in this, what you'll do is you'll completely evaporate all the solvent so that your photoresist layer becomes hard. Then we'll follow this by inspection and etching. In etching, what happens is whichever region is not protected by the photoresist will get etched. So whichever region, this particular region will get etched. Then we will remove the photoresist and then we'll have a patterned layer. So in the case of metal deposition, you will have a different kind of structure, whereas in the case of etching, you're having a different kind of structure that is finally formed. Is this clear? Any doubts? Any doubts? Do you want me to repeat again anything? So we also have so the previous process flow that we saw, that was for a positive. So next we have different exposure modes. So one is the contact mode of exposure. So in this, like here, as you can see here, you have a mask which is having close contact with that of a silicon wafer, which is coated with a photoresist. So here, if you compare the resolution, then next we have a proximity mode where we have the mask which is placed in proximity with the sample. So there is some small distance, and this distance can be generally in the range between 5 micrometer to 50 micrometer. In the case of projection mode, uh, like there will be a large distance between the mask and the sample. So between the mask and the sample, you will have a separate objective lens. This objective lens will again control the diffraction of light from the sample. Sorry, it will control the diffraction of light from the mask, and it can be manipulated so that we can get like smaller features on the sample as compared to the mask. So if you compare these three types of exposure modes in terms of resolution, your the projection mode will give you the best resolution. So it can be smaller than your mask size by having a suitable objective lens optics. So critical dimension is something that we use to tell the smallest feature that we have on a mask. Contact mode will have, so this is the smallest critical dimension. Contact mode will have larger critical dimension than that of the projection mode. And proximity will have the largest dimension for the same mask pattern. So how and why is this? This is because here you can see that the mask is at some particular distance from your wafer. So your light will get diffracted. So by the time it reaches your photoresist, the light might have spread out a bit. So the features that you get will be bigger than that of your mask. When you are doing contact lithography, what will happen is your features can be exactly same because there is no like space for the light to get diffracted. In projection lithography, you are using objective lens to again focus the light, so your features can be made smaller than that is present in the mask. And when you are making a mask, you will try to make it use it for mass production or batch production. So in that case, like if you are using the mask for proximity or projection lithography, then it can be reused multiple times. However, when you use the mask for contact lithography, what will happen is your mask will come in contact with photoresist. So your mask will get covered with a little bit of photoresist. So it has to be cleaned before you do the next exposure. As a result, the life of that mask will be somewhat lower. Again, in the mask, there are two types of masks that can be used. One is the mask can be made using soda lime glass, and more expensive masks are made using quartz. So generally, like less expensive masks are made using soda lime glass. More expensive masks are made using quartz, and the pattern that we see in the mask, the opaque pattern is generally chromium metal. Is this clear? Any doubts in this till this point? When we are trying to, generally we will not go for just one layer, right? We may have multiple layer of materials. So if you are having silicon, we may have SiO2 on top. Then we can have some metal layer on top. Then we will have another SiO2 and you can have another layer of metal. So in class, you would have seen something called as like where we have IDE and heater below it, right? So the if you look at the cross section of the material that is present on that particular structure, it will look something like this. Where you have SiO2 between the metal in order to prevent the metal from being short, because SiO2 is an insulator. It is both electrical as well as thermal insulator. So it will not allow any electrical contact between the two metals. And silicon, we don't want any electrical contact between the metal and silicon as well. So we will also have some SiO2 in between. When we are, if we are just going for one layer of patterning, then we can just use a mask and we can make our desired patterns on the wafer. However, when we want to do multiple patternings on this particular sample, we have to align with respect to the previous layer. So let's say if I am doing, first I am taking silicon wafer, okay, I am depositing SiO2, and in the first process I have to do etching of SiO2, so I will go for lithography. I have some patterns on my wafer, I've transferred the patterns, and then etching is carried out. After etching, what happens is my SiO2 layer will look something like this. So I would have removed SiO2 in some regions where I don't want, and like in regions where I want, SiO2 will be there. Next, if we are going for metal deposition, there also we want to deposit metal in some regions, whereas other regions we don't want to deposit metal. So let's say if you want to deposit metal only in this region, we have to make sure that when we are aligning the mask with the rest to the sample, that our patterns do not get written somewhere else, right? So for that reason, we will be using alignment markers. So this alignment marker can be used to align your current layer with respect to your previously written layer. So we also saw different kinds of shapes can be used for alignment markers. However, we generally don't go for circle alignment marker because it can tell us like whether there is X displacement or Y shift is there, but it cannot tell us whether the sample is rotated or not. So if we go for alignment markers which have corners like this square, then we can tell whether the sample is rotated or it has X or Y displacement. So here you can see three different patterns on the same mask. So now you can tell which is correctly oriented, which is having some rotation and so on. So here among these patterns, which is having shift like X or Y shift? Which pattern is having X or Y shift only? Can you tell which pattern is having X or Y shift? Are you there in the meeting? Okay, so here, ideally we want this black color square to be exactly in the middle. So this is correctly aligned. This is also correctly aligned. This is having X shift. These three are having X shift. Here you can see that this pattern is correctly aligned, but all the other patterns are shifted either in X or Y direction. So this is having rotation shift. That is, it is rotationally misaligned. This one is having shift in X direction. So your samples are shifted in this direction, translation shift. So your sample can be really big as well, right? When we just see alignment marker at one point of the sample, it may be aligned, but at the other point also it should be aligned. So what we will do is we will have alignment markers at different portions of the sample. We will check whether it is exactly aligned at each of these points. So since we have multiple points, if we can ensure that there is proper alignment at each of these mentioned points, then your sample, the other patterns will be properly aligned. So when we will generally have more, not only one alignment marker, but more alignment markers which are placed at various portions of the sample to ensure that your pattern is correctly transferred. So in this case, this is your metal and this is SiO2. What happens if if there is misalignment, the metal will come in contact with silicon. Okay, so that is not what we want. That's why we have to ensure that there is proper alignment when we are doing this. Okay. Other than square, a pattern like this can also be used as a alignment marker X. So any pattern which is having sharp corners or defined corners can tell us whether the with respect to the previous layer it is aligned or misaligned. So that's why we go for these kind of markers. And another content that we saw was residual stress in films. So like in one of the course lectures, we had a scenario where the released cantilever was it was bent. So that was because there was SiO2 deposited on the cantilever, and the SiO2 was undergoing. So you know that silicon dioxide has compressive stress, right? So that means that SiO2 is compressed, but in order to release the stress, it will try to expand. So what happens is when you release the cantilever, SiO2 will try to expand. However, like if there is some stack beneath it, let's say it is something layer of silicon, that will not have any stress compared to SiO2. So when silicon dioxide tries to expand, silicon will not try to expand. So your cantilever will kind of get bent in this fashion. If we look at silicon nitride, Si3N4 or Si, depending on the stoichiometry, your silicon nitride, certain stoichiometry of silicon nitride can have tensile stress. Tensile stress means it has positive stress. Your like this case, your film will try to, it wants to expand, but it is not being allowed. Uh, Sorry, it is being stretched. When your film is on the substrate, it is being stretched. So what happens is when you try to release the substrate, what happens is your film will try to contract. So your cantilever will bend, something like this. Okay. By having different stacked materials of silicon dioxide and silicon nitride, we can ensure that the two stresses can get cancelled out. So when you release your cantilever structure, you will have a straight cantilever. So for this, what we will do is we have to adjust the thickness of SiO2 and silicon nitride respectively. So next we will move on to dry etching process. Like in etching, there are two different types. One is wet etching and the other is dry etching. So in wet etching, we will use chemicals to etch the sample. So what happens is chemicals will come in contact with the sample. It will react with the sample, and the etching will happen. The byproducts will get removed from the sample. So in wet etching, there are two types. Either the etching can be isotropic or it can be anisotropic. So in isotropic means it will etch equally in all the directions. So let's say if you're having a film like this on your, so this is your film that you want to etch. If it is isotropic, if it is etching here in thickness T, it will also etch in thickness T in this. So your profiles will get somewhat rounded. It will etch equally in lateral direction as well as in vertical direction. In anisotropic etching, what will happen is your vertical direction will have different etch rate compared to your lateral directions, and also this anisotropic etching is generally seen in silicon. So where you have different planes, right? 100, 110, 111, and so on. So if you are trying to etch your silicon with either KOH or TMAH, which are alkaline based etching solutions, then what will happen is, depending on which surface your alkaline solution sees, the etch rate will be different. So here your 111 is generally etched off for the KOH. So it will etch in 100 and 111, so 110 directions. So like depending on whether you have 100 wafer or 110 wafer or 111 wafer, your etch profile will become different. Okay. And for isotropic etching, we generally use acid-based etchants. So this is wet etching. In dry etching, also we have both isotropic and anisotropic etch profile. So before that, etching is generally used to remove material selectively. Like we want to remove, if you're having multiple stack of materials, we may want to remove only one particular stack of material without affecting the other materials as well. Okay. So in isotropic etching, what will happen is, here by using dry etching also, where we use plasma or gaseous reactants, and like we can also use some kind of ions that are generated to etch the sample. If we are using gases such as BRF3, xenon fluoride, or ClF3, if you are using any of these three gases, you will get a isotropic etching. If you are using plasma, which is fluorine based, like CF4 or SF6, you can get anisotropic kind of etching. So in dry etching process, it is not sensitive to your not sensitive to crystal orientation. In wet etching, in anisotropic etching, you saw that depending on your crystal orientation, your etching rate will be different. However, in dry etching, irrespective of whatever crystal orientation you have, whether you use 100 wafer or 110 wafer or 111 wafer, your etching rate will not be determined by that. So, depending on what chemistry you are using, you can get either a isotropic profile or a anisotropic profile. So, is this clear? And in etching, there are certain terms. Okay, one is etch rate. So etch rate is rate at which the material is getting removed. Then another thing is anisotropy and selectivity. So these are the important parameters in your etching when you are doing etching. So what is anisotropicity? Anisotropicity is if you are having something like this, this is your depth D. So here you can see that even though your edge opening may be this much, there will be some additional region which is etched on the side. So this is anisotropic profile. Why? Because like you can see that the edge depth is different in vertical direction as well as in lateral direction. So let's say this is your lateral edge. We are giving it by W. This is your pattern width. Okay, TP. Then in this case, your anisotropicity is given by 1 minus lateral edge by vertical edge. So your lateral edge is W divided by D. So there is also another thing called selectivity. So selectivity is rate of etch of desired material So these are two terms that will generally come uh, in etching. So like I told you, right, there is two types of etching. One is isotropic or anisotropic. If it is isotropic etching, what will your anisotropicity be? If you are having a isotropic etching profile, what will be the value of anisotropicity? No, what number will it have? Like number can vary any values between. It can be. What is the condition for isotropicity first? Then, if your H profile is isotropic, how much will be your lateral HP, or how much will your vertical HP? Is a question that I'm asking clear? Okay. So if you're having isotropic H profile, like what will be the relation between your lateral edge and vertical edge? The H profile, right? So Am I going too fast? So when you are etching, like either there are two different kinds of profile. Okay, one is isotropic etch profile, and the other is anisotropic etch profile. If it is isotropic, what happens is your vertical etch rate and your lateral etch rate will be the same. Okay, so if your vertical etch rate is H is D, lateral etch rate is W, then it will be the same. What will happen is your profile will be like this. Okay. So it will have equal H in all the directions. This is isotropic. If it is anisotropic, and let's say your vertical H rate and your lateral H rate will be different. So there can be two cases. One case where your vertical H rate is very much high. So what happens is your vertically it will etch more, lateral H rate is less. Okay. So you will have something like this. So this will be your lateral edge and this is your vertical edge for this particular pattern. And there can be another case where your lateral edge is too much high, but your vertical edge is less. So this is generally unideal condition which we don't want. So what happens is here your pattern will come like this, right? So this is anisotropic. There is also another case where you don't have any lateral edge at all. So in that case, you can say your pattern is like this. Okay, so you have this is case A, this is B, C, D. So in each of these cases, what will your anisotropicity be? Anisotropicity is given by this formula. Okay, case 1 will be 0. Yes, correct. For case 2, in case 2, your D is very much high compared to W. Yes. So case 2 will be less than 1. It will be close to 1. Case C, case 3, which is this one. Yes, case 3 will be far from 1, but it will be also negative because your W is will be larger than your your lateral edge rate is larger than your vertical edge rate. Okay. Then for case D, case D it will be 1. Yes. Okay. So if you want, like ideally the for a very ideal edge, we'll have anisotropicity of 1. Okay. So this is regarding anisotropicity. Regarding selectivity, I will ask one question. So if your selectivity is greater than 1, is it desired or it is undesired? What value of selectivity is desired? Is it greater than 1, less than 1, or 0? Which value is desired when we are doing etching? Our numerator should be greater, right? So this will hold not only like for, I will explain two cases now. One case is we are having uh, SiO2 here, and then we are having silicon here. Okay, silicon, and then we are having PR on top. So here your undesired material will become PR and your silicon. So like you can tell selectivity of photoresist with respect to SiO2. So that will be rate of etch of SiO2 divided by rate of etch of undesired material. And also you can say selectivity of SiO2 with respect to silicon, where SiO2 is your desired material and silicon is your undesired material. Because when you are trying to etch SiO2, you want to etch only SiO2, you don't want to etch anything else. Okay. So it will not just, it will include the layer above as well as the below when we are considering the selectivity of the material. This is clear, right? So next we will generally look at dry etching process. So this is the general like diagram of how a dry etching process will work. So in dry etching process, we will generate a plasma, and gas species will be allowed to flow through it. So this gas species will get ionized in the plasma, and it will form different HN species. Sometimes it will form like some reactive ions as well. So this HN species will first get diffused to the surface of the wafer. If there are any like reactive ion species that is present, that is if you are using fluorine based plasma, then if there is any F plus ions or something that is present, those ions will get bombarded. And in some cases we can use plasma like argon based plasma. So if you are using argon based plasma, we can also generate argon ions. So these ions can also be used to bombard the surface. So that is one way by which we can etch the material. Another way is we react the surface of the material with any reactive ions or molecules that are present in the gas. So if you are using any molecules to react, that is like chemical based etching, but it is dry etching process because we are not using wet chemicals. If you are using reactive ions in order to etch the material, then it is reactive ion based etching, which is also called as RIE for short, reactive ion based etching. There is also dry chemical based etching. So in chemical based etching, in some cases, they will not use any plasma at all. There is also ion bombardment etching, so where we have some kind of plasma which is formed using argon ions. These argon ions will get excited by the voltage that is applied between the top and the bottom electrode, and they will bombard the surface of the wafer. So if there is any HN species that is present, which will chemically react with the material to form the various byproducts, it will first get diffused to the surface, then it will get absorbed on the surface, it will react with the material, some byproducts will be formed. These byproducts will get desorbed by the surface and then they will get removed. So this is the general process by which etching will happen. So like and this etching can be used to etch various materials. It can be used to etch dielectrics. It can also be used to etch silicon as well. However, like if you want to go for very deep aspect ratio structures, then this process is not like helpful for getting deep aspect ratio structures. So aspect ratio is what is the aspect ratio? Aspect ratio is the ratio of the depth to the width. So it is the ratio of width to the height. So if we are having larger aspect ratio structures, what we are having is we are having very deep trenches. So for modified process where we have like two different kinds of gases. So the first is C4F8. What this will do is this will deposit a polymer. We have SF6 which will etch silicon. So if you are starting with a pattern like this and we are having photoresist here, then first in the first step a polymer will get deposited, so it will get deposited everywhere. Then in the second step SF6 gas will be passed through, and also some amount of bias will be given, so the etching will start to happen. So SF6 will etch more in the vertical direction compared to the lateral direction. So what we will have is after some time we will have some amount of etched silicon and we'll have PR. However, the polymer that is deposited on the side walls will be still there. So this will be still there. So here your side wall is getting protected. So in the next cycle, uh, what will happen is we will go for again deposition of polymer. This is then followed by the etching phase. So in etching phase, what will happen is we'll again etch some more. So like when we do multiple cycles of this etching and deposition phase, what we like are finally having is a structure like this. So these are called as scallops. These are characteristics of the samples which are etched using the Bosch DRI process. So DRI here stands for deep reactive ion etching. So by doing multiple cycles of polymer deposition and etching, we can ensure that we are having a large aspect ratio. So small width with larger depth. So generally for BOS DRI process, the aspect ratio can be between 1 to 10, 1 is to 10 to 1 is to 20 in some cases. Mm. We looked at some etching processes, right? There are also some thin film deposition processes that we had shown in the lecture. So we can generally classify this into two. One is physical based, and another is chemical based deposition methods. So which are the types of physical based deposition methods? What are the physical deposition techniques that you have seen? Now, what is so you would have seen physical vapor deposition, right? So we have two different kinds of thin film deposition techniques. One is physical vapor deposition, another is chemical vapor deposition. This is CVD, this is PVD. So in physical vapor deposition, what we do is we use physical means to vaporize the sample, to convert sample into vapor, like whichever material that we want to deposit. So for this, we have two kinds of methods. One is sputtering and the other is evaporation. So in sputtering, we can sputter metals. We can also sputter dielectrics. So for dielectrics, generally we do some sort of we can do either direct sputtering or we'll do some sort of reactive sputtering. In the case of evaporation, we have two different kinds of techniques. One is thermal evaporation and the other is E-beam evaporation. So in thermal evaporation, what we'll do is we'll have a heating filament below the crucible. We'll pass current through the filament, and like as current flows through the filament will have some amount of resistance, so it will get heated up due to Joule's heating effect. This will melt the crucible. So what happens is then your crucible will so it will melt the material in your crucible. The material in your crucible will get evaporated, and if your substrate is mounted here, it will just the vapors will uh, fall on the surface of the substrate. So this is what is happening in thermal evaporation. In E-beam evaporation, what we'll do is we will use electron beams to evaporate the material. So if you're having crucible here, you will use electron beam, and with the help of magnetic field, you will focus the electron beam to fall on the crucible and melt the material. Your vapors from the material will fall on the substrate. So here, so this is generally a line of sight deposition process. The vapors will travel in straight phase. In case of sputtering, it is not much of a line of sight deposition process. So in sputtering, what happens is you will have argon plasma, and you will have your target here. So this target will have the material that you want to deposit. Your substrate will be present here. So your argon ions will bombard the target, and it will like cause atoms or molecules to come away from the target. So this will then fall on the substrate and it will get deposited. Okay, so this is what happens in sputtering. In the case of sputtering, it is not like line of sight, as your atoms can move in different directions depending on how your argon ion is coming in contact with your target. So let's say if you want to do metal deposition, and if you are having a photoresist like this, we want to do deposition and metal deposition plus liftoff. Then if you are going for sputtering, so your metal will get deposited here, it will get deposited here. Okay. It will also get deposited in the side walls. So when you're trying to do lift off, like it will not be very, in some cases, if your metal deposition is not done good, there'll be contact formed between the top and the bottom surface. However, if you go for evaporation, since it is line of sight, your metal will get deposited in this region, and in this region. It will not get deposited in the side walls. This is the difference in how the metal deposition happens between sputtering and evaporation. So then we also looked at chemical vapor deposition. So in chemical vapor deposition, what we will do is we will pass like we will make the chemical vapors react to form like deposit different compounds. So there are different types of chemical vapor deposition. One is LPCVD, APCVD, PCVD. So APCVD is atmospheric pressure chemical vapor deposition. So here the deposition is done at atmospheric pressure. Generally in this CVD, the chemical vapor deposition techniques, we control the pressure and temperature to ensure uh, so in CVD techniques, APCVD, LPCVD, and also you have something called as PCVD. So in APCVD, the reaction happens at atmospheric pressure. Here the reaction happens at low pressure. This is plasma enhanced CVD. So in chemical vapor deposition techniques, two of the main important variables that we control to bring about the deposition process is pressure and temperature. So in atmospheric pressure CVD, the pressure is large, so the temperature also will be somewhat high in order to bring about the reaction for the deposition process. In the case of low pressure CVD, the temperature will be, it can be, the deposition process can happen at somewhat lower temperature. However, in both of these processes, in order to bring the chemical vapor deposition to happen, what we have to do is we have to supply the energy by means of the temperature in the system. So generally, the temperature at which this reaction happens will be greater than 800 degrees centigrade. If we want to do deposition of chemical vapor deposition at a lower temperature, then we can go for PCVD. PCVD is plasma enhanced chemical vapor deposition, where we provide the energy for the reaction to happen by using plasma. So your temperature that you have to supply to the system can be low. So it can be low as 200 degrees centigrade to 400 degrees centigrade. These both will need very high temperature. So this is chemical vapor deposition technique. So there is also another technique called as ALD. ALD is atomic layer deposition. So in chemical vapor deposition, what will happen is first we will pass the precursor A, which is the reactant A. Then we will pass precursor B. So we'll have a sample here. Okay. When both the precursors reach and when suitable amount of energy is given to the system in form of temperature, uh, the precursor A and B will react, so it will form some byproducts. That byproducts will get deposited on the wafer surface. So that is how your chemical vapor deposition happens. So here both the precursors will be at the same time. However, in order for the reaction to happen, we have to supply some energy in terms of temperature. In the case of PECVD, we will supply this energy by means of the plasma. In case of atomic layer deposition, what will happen is first we will so in atomic layer deposition, as the name suggests, we are depositing atomic layer by layer. So if we are having two precursors A and B, which will react us to form our atomic layer, first we will pass precursor A. So what will happen is, if this is your substrate, first is your precursor A is passed. So this will react with your substrate and it will form some kind of bonds. So it will form some self-limiting kind of surface on your substrate layer. Then we will purge the system. So during the purging process, what will happen is we will completely remove all traces of precursor A except the ones which are linked on this substrate. So, so earlier when we are passing precursor A, we may have some remnants of precursor A in the gaseous form. However, when we purge, the whichever precursor A has reacted with the substrate to form some kind of compound, it will remain. And then we will pass precursor B. So what will precursor B do is it will react with A. It will not react with any other surface. So B will react with A to form the compound. So only on the surface we'll have your final compound. Okay. So here only on the monolayer that is formed on the substrate we will be able to find the deposited layer. And this technique is chemical vapor deposition because we are reacting two chemicals to form a particular film. However, this will give us some range of few nanometer thick films. So some metal oxides can be deposited by using atomic layer deposition. So in chemical vapor deposition, we can go for a few hundreds of nanometers of films. But in the case of atomic layer, it will be like few nanometer. I think this covers most of the uh, content that we have covered in the course regarding fabrication. Any questions? Uh, yes. So that's all for this session. Thank you. Yes.